This is 3i Atlas. This is Mars. 3i Atlas is about to swing by, and a fleet of camera-ready rovers and orbiters are standing by to snap some pictures.
The James Webb Space Telescope had already revolutionized human understanding of the cosmos, but its latest discovery shook the very foundations of what scientists thought they knew about life and its place in the universe. The event began with a quiet alert deep within the data streams coming from Webb's near-infrared spectrograph, an instrument capable of identifying the faintest chemical fingerprints drifting through space. The target was the interstellar object 3i Atlas, a mysterious traveler not native to our solar system, first observed streaking through the outer regions in late 2024. Its trajectory, strange and precise, had already intrigued astronomers. But when Webb's sensors detected spectral patterns unmistakably associated with biological processes, the scientific world erupted. Before we start, hit the like and subscribe buttons for more exclusive news. At first, the team thought it was an error, a calibration issue, a glitch in data processing, or perhaps the interference of cosmic dust confusing the sensors. Webb had detected methane, carbon dioxide, and water vapor on many worlds before, but the ratios this time were off. They followed a pattern of metabolic balance, one that mirrored the gaseous byproducts of microbial ecosystems on Earth. Even more astounding was the simultaneous detection of complex organic molecules, including amino acid precursors within the coma, the halo of material that surrounded 3i Atlas as it neared the warmth of the sun. No comet or asteroid ever studied had carried such a diverse, organized molecular signature. It wasn't just chemistry, it was biochemistry. The news moved quickly from the control rooms of the Space Telescope Science Institute to international observatories and space agencies around the world. Webb's findings were verified, then re-verified. The comet-like object 3i Atlas wasn't just an inert interstellar rock. It was a vessel carrying active organic material, possibly microbial life, preserved within its icy layers for eons. The discovery didn't just expand the definition of habitability, it demolished the assumption that life required a stable planet to emerge or endure. Here was an interstellar traveler, forged in a different star system, bearing the signs of life as it glided silently toward the inner solar system, and toward Mars. The scientific community's response was electric. Astrobiologists, exoplanetary chemists, and cosmologists all converged on the data, dissecting every wavelength of light Webb had recorded. The patterns were consistent with the presence of phosphine, nitrogen-bearing molecules, and traces of lipid-like compounds, elements of cellular membranes. Some spectral spikes even hinted at the presence of chlorophyll-like pigments, the kind associated with light-harvesting organisms. If confirmed, it would mean photosynthetic, or at least photoreactive, life had evolved beyond Earth. The implications were staggering. Life could arise not only independently across the galaxy, but also survive the unimaginable journey between stars. As 3i Atlas continued its path inward, the object's orbit was recalculated with increasing precision. It was on course to pass close to Mars, within a few 100,000 kilometers of the planet's orbit, a proximity that made every planetary scientist sit up. The possibility that Martian gravity might capture a fraction of the material ejected from its coma, or that microscopic life might seed Mars's thin atmosphere, transformed the discovery from a scientific curiosity into an existential question. Was humanity about to witness the first known instance of panspermia? The transfer of life between star systems? Webb's infrared eyes, positioned 1,000,000 miles from Earth, continued to track the object with relentless precision. Images showed a shimmering tail forming as sunlight began to vaporize the outer ice layers. Embedded in that tail were organic grains reflecting light in a pattern unlike any comet known. Even the motion of the coma seemed peculiar. It pulsed rhythmically, as if venting gases in intervals suggestive of regulation rather than randomness. Some speculated about cryovolcanic vents, others about internal pockets of reactive material releasing bursts as they thawed. But for a small group of astrobiologists, there was a more daring hypothesis: biological control. Could the organism, or whatever it was, be responding to the sun's radiation? The idea seemed preposterous at first, yet Webb's data continued to defy expectation. The object's albedo fluctuated subtly over time in ways that mirrored diurnal cycles on Earth. It was as though the material on the surface was changing reflectivity based on exposure, darkening under direct light, brightening in shadow. Such adaptive behavior in a frozen interstellar body was beyond any known physical mechanism. A pattern of faint polarization in the reflected light hinted at structured molecular alignment, a hallmark of biological membranes or crystalline protein complexes. The boundary between mineral and organism was blurring. The object itself was enormous compared to typical comets. Nearly 400 meters across, a fragment of something larger that might have once circled another sun. Its composition was ancient, the isotopic ratios suggesting it had formed in a star system with a different metallicity than our own. The idea that life could emerge in such an environment and survive the interstellar void for millions of years opened questions no philosopher or theologian had ever dared phrase. How many such travelers might have already passed unseen through our skies, seeding worlds in silence? The proximity to Mars added urgency to every new observation. Mars, already known to harbor traces of subsurface ice and ancient riverbeds, represented a fragile bridge between Earth and the wider universe in humanity's imagination. If 3I Atlas indeed carried viable microorganisms, its near pass could change the planet forever. Scientists modeled scenarios where dust from its coma might settle on the Martian surface, mixing with existing regolith or subsurface water vapor. A biological exchange, however minute, would mean that life was no longer confined to Earth's biosphere. The Martian environment could become a natural laboratory for alien biology. The event also forced a reconsideration of planetary protection protocols. Humanity had long worried about contaminating Mars with Earth microbes. Now the inverse seemed possible. If life from another star system made contact with a planet within our own, it could rewrite the genetic and evolutionary narrative of two worlds. Some argued that 3I Atlas was a cosmic courier, delivering genetic templates that once seeded life across the galaxy. Others viewed it as a natural experiment, a glimpse into how life survives beyond planetary boundaries. The public fascination was immediate and overwhelming. As Webb's findings circulated, news outlets filled with artist renderings of the comet gliding past Mars, trailing streams of luminous blue vapor. The thought that microscopic life could be riding those particles, perhaps dormant, perhaps active, transfixed millions. Humanity had searched for aliens among the stars, never suspecting that the first proof might arrive not as radio signals or distant civilizations, but as microscopic voyagers embedded in ancient ice. It was humbling and terrifying all at once. Within scientific circles, debates raged over what life truly meant in this context. The data did not yet prove that the material was living in the active sense, replicating, metabolizing, adapting, but it suggested organization and chemical stability far beyond abiotic chance. Some proposed that 3I Atlas carried protocells, chemical systems that teetered on the edge between living and inert. Others speculated about dormant spores, preserved for millions of years by radiation-resistant shells. The most radical voices imagined an entirely different biochemistry, perhaps silicon-based or reliant on exotic solvents that had long since sublimated. Whatever it was older than Earth itself. As more instruments turned their attention to the visitor, new layers of mystery emerged. The European Space Agency's Gaia Observatory detected faint electromagnetic fluctuations near 3I Atlas, as if certain frequencies of radiation were being absorbed and re-emitted in patterned intervals. Some thought it was a natural resonance effect, caused by crystalline lattice vibrations. Others dared to whisper the unthinkable, that it might represent a primitive form of signaling, an organic response to stellar radiation. The concept of a comet responding to light stretched the limits of imagination, yet the numbers persisted. The trajectory analysis predicted that the object would pass within 0.03 astronomical units of Mars, close enough that some of its outgassing material could intersect the Martian atmosphere. NASA's orbiters around the planet began preparing to monitor the event. The Mars Reconnaissance Orbiter and MAVEN mission adjusted instruments to capture atmospheric changes. The Perseverance rover, far below in Jezero crater, stood ready to analyze dust and air samples for any anomalous chemistry. Humanity was about to conduct, by pure cosmic accident, the first interstellar life encounter. Back on Earth, Webb's instruments refined their data. The spectral analysis now showed cyclic fluctuations in methane and oxygen ratios, an unmistakable metabolic signature. It was as though the material on the surface was breathing, consuming and releasing gases in response to solar input. No non-living mechanism could replicate that behavior so precisely. Astrobiologists began drafting theories. Perhaps the comet's internal matrix harbored microbial colonies that thawed as it neared the sun, metabolizing short bursts of energy before refreezing. Each flare of life was brief, like the pulse of a deep-sea organism rising toward the light before retreating into darkness. Speculation spread through every scientific discipline. Could 3I Atlas have originated from a habitable moon orbiting another star? Did it once serve as an icy ark, preserving the biosignatures of a lost world? The isotopic ratios of oxygen and hydrogen hinted at an origin around a cool red dwarf, a system rich in volatile elements but exposed to high radiation. If life had evolved there, it would have needed to adapt to extremes, perfect training for survival across the interstellar void. Perhaps 3I Atlas was not a survivor of chance, but a deliberate ejection, a fragment flung outward by cataclysm or purpose. The closer the object came, the more vividly Webb and ground-based telescopes captured its changing face. Jets of vapor erupted from fissures, shimmering against the blackness. Within the jets, spectroscopy revealed carbon chains twisting in complex patterns, resembling polymers used in biological scaffolding. Each observation deepened the sense of awe. The cosmos, once seen as indifferent and sterile, now shimmered with hidden vitality. 3I Atlas was not just another visitor, it was a messenger from the galactic ecosystem. Philosophers began to speak of it as a mirror for humanity's place in the universe. If life could emerge independently across the stars and traverse the darkness between them, then existence itself was no longer an anomaly. It was a cosmic constant. Life, in that vision, was not bound to planets, but to the fabric of the universe itself, carried on icy vessels and dust trails, seeded by the chaos of creation. Every supernova, every collision, every wandering comet might be part of an immense interconnected web of biology stretching across light years. Even the timing of the event seemed poetic. As 3I Atlas approached Mars, human exploration of the red planet was entering a new phase. Robotic missions were preparing for sample return, and plans for the first crewed missions were solidifying. The possibility that Mars might already host alien microorganisms, delivered not by human hands but by a visitor from another star, blurred the line between discovery and destiny. If life arrived there just before humanity, what would that mean? Would Mars become a shared world, a convergence point for two forms of life from different origins? For all its grandeur, the discovery also stirred unease. If interstellar life could survive and spread through natural means, it meant that the cosmos was not a sterile playground, but a living ecosystem, and ecosystems have predators, parasites, and competition. Scientists cautioned against romanticizing the find. The resilience of 3I, Atlas's microorganisms, if they existed, might make them formidable survivors. Their biology, shaped under alien suns, could operate with chemistry incompatible or even hostile to terrestrial life. The thought of an encounter between Earth and such entities was both thrilling and terrifying. Yet, amid the speculation, one truth became undeniable. The James Webb Space Telescope had achieved what generations of instruments before it had dreamed of. It had glimpsed the fingerprints of life beyond Earth. Not in radio waves or ancient ruins, but in the faint glow of molecules drifting through space. Humanity was no longer alone in theory. It was connected in evidence. The light from 3I Atlas carried more than data. It carried the story of life's persistence against cosmic odds. In academic halls, papers poured forth, each more daring than the last. Models of interstellar biology, simulations of panspermia across galactic arms, and genetic stability studies filled the literature. Some proposed that Earth itself might owe its origins to such travelers, that the very DNA encoding humanity's story could be the echo of long-lost interstellar visitors. The circular symmetry of the revelation was profound. Perhaps life on Earth had begun just as life on another world might soon begin on Mars, seeded by a wandering emissary from the stars. Telescopes worldwide coordinated to follow 3I Atlas as it drew closer to Mars. Observatories in Chile, Hawaii, and orbiting platforms like Hubble joined the effort. Together, they formed a planetary-scale symphony of observation, capturing every spectral shift, every burst of light. The data flowed into global repositories accessible to researchers across nations, united by a single humbling mystery. It was not merely a scientific campaign, it was a vigil. The days following Webb's final confirmed observation of 3I Atlas became an age of reflection, not just in laboratories or observatories, but in the collective consciousness of humanity. The discovery had done something no single event in modern history had managed. It united people across nations, ideologies, and faiths under a single question that transcended politics or creed: what does it mean to share the universe? The recognition that life, however microscopic or alien, had existed beyond Earth and was now moving past Mars, transformed humanity's perception of itself. Astronomers who had devoted their lives to lifeless orbits and silent stars suddenly found themselves gazing at an animated cosmos. The cold, mechanical universe once imagined by materialists now appeared as an intricate web of vitality filled with unseen biologies drifting like cosmic seeds. Philosophers revisited ancient notions of the living cosmos, once dismissed as mystical metaphor. The Greeks, the Stoics, even early Hindu cosmologists who spoke of worlds born and reborn within an eternal organism, all seemed suddenly prophetic. The scientific mind had collided with ancient intuition, and for the first time, the border between the spiritual and empirical seemed porous. In the scientific community, the debates grew ever more intricate. Some insisted that calling the organic material life was premature. Perhaps it was merely a unique form of self-organizing chemistry frozen in time. Others argued that self-organization itself was the essence of life. The discovery forced biologists to revisit the very definitions of vitality, metabolism, reproduction, evolution. What if life did not need all three? What if it existed in gradients, from chemical resonance to sentient awareness, all part of one spectrum of being? 3I Atlas blurred every line. It was not alive in the human sense, nor entirely inert. It pulsed at the boundary, half asleep in the shadow of starlight. The data from Webb continued to be studied in immense detail. As processing algorithms improved, new spectral features emerged, tiny peaks of unknown origin in the mid-infrared range. These could not be matched to any terrestrial or known interstellar compound. One of them showed periodic shifts, as if its source was changing over time. The signal was subtle but unmistakably rhythmic, like a heartbeat echoing through light. Some suggested it was due to rotational changes in the comet's structure. Others whispered that it might be a biochemical cycle, a kind of metabolic rhythm frozen into its ice. The mere suggestion that metabolism could occur in a body traveling between stars opened questions so profound that entire research institutions reoriented their missions around it. The world's space agencies quickly established joint task forces to monitor and model potential outcomes of the comet's passage. NASA, ESA, JAXA, and ISRO shared data seamlessly, abandoning their usual rivalry in a rare act of global unity. The purpose was no longer competition, it was comprehension. Mars, once just a scientific frontier, was now a potential site of contact between two biologies. Observations from orbiters began to detect faint atmospheric variations around the time of 3I, Atlas's closest approach. Tiny surges in methane, localized near the planet's equator, appeared hours after the comet's material brushed the upper atmosphere. The coincidence was too sharp to ignore. The scientific community hesitated to call it proof, but the implications were irresistible. If fragments of 3I Atlas had indeed mingled with the Martian environment, then Mars had ceased to be an isolated world. For the first time, a celestial bridge had been formed between life systems of different origins. It was as if the galaxy itself had performed an experiment, showing humanity what cosmic ecology truly looked like, a dance of exchange, where even the void between stars could be fertile ground for transfer. The principle of panspermia, once considered fringe, now stood as a central tenet of astrobiology. Life was no longer bound to the soil of planets, but to the tides of the cosmos. The philosophical ripples reached far beyond the scientific community. In universities and temples alike, thinkers grappled with what the discovery implied about consciousness. If life could endure between stars, frozen for millennia and revived by warmth, perhaps consciousness itself was a continuum. a field that life merely tuned into rather than created. This thought was not new, but it now bore a new kind of legitimacy. The universe was no longer an empty canvas upon which life briefly flickered. It was an organism breathing across eons. Humanity, with its telescopes and theories, was merely the latest expression of that breath. Artists found themselves inspired in ways unseen since the Renaissance. Paintings and holographic sculptures depicted 3I Atlas as a luminous voyager carrying the seeds of creation. Poets spoke of it as a messenger between stars, a silent pilgrim bearing the DNA of forgotten worlds. In music, composers began crafting symphonies based on the comet's orbital harmonics, turning its mathematical path into haunting melodies. The arts became the emotional counterpart to science's revelation, a way for human emotion to translate the enormity of cosmic truth. Meanwhile, scientists worked tirelessly to build physical models of how life could have persisted aboard the comet. In laboratories simulating the conditions of interstellar space, researchers recreated the frigid temperatures and radiation exposure 3I Atlas had endured. Certain extremophiles from Earth, tardigrades, bacterial spores, and lichen, demonstrated astonishing survival under these same conditions. The experimenters noted that ice, far from being hostile, could act as a perfect shield against radiation, preserving organic complexity over unimaginable timescales. The very structure of a comet, porous and layered, might serve as a natural arc. This idea ignited an even more profound hypothesis. Perhaps comets were not mere byproducts of planetary formation, but essential components of the galactic biosphere. Mechanisms through which life propagates and renews itself. Each star system, upon forming, might eject icy fragments filled with its unique organic signatures. These fragments would drift through interstellar space, occasionally seeding new worlds with their contents. Life in this vision was not a miracle of one planet, but the inevitable consequence of stellar birth and death. The galaxy itself was an ecosystem, its comets the spores of cosmic growth. As models of 3I Atlas's journey were refined, its origin grew clearer. Astronomers traced its trajectory backward through time, reconstructing its path across the Milky Way. The results suggested that it had originated from a region near the constellation Cygnus, an area dense with young stars and molecular clouds. Some even pointed to a specific system, a red dwarf surrounded by multiple exoplanets, one of which was suspected to have liquid water in its early history. If 3I Atlas had indeed been born there, it might have once circled a living world. Perhaps that world had long since perished, its biosphere shattered by cosmic disaster, its remnants cast into eternity aboard fragments like this one. In that sense, the comet was not just a wanderer, it was a survivor. There was a certain poetry in that possibility, that the death of one world could give life to another. The atoms in the comet might once have formed the bodies of creatures long extinct, their essence carried across space to spark new genesis elsewhere. The concept that death and creation were part of one galactic cycle resonated deeply with humanity's oldest myths. Even in the sterile precision of astrophysics, there was something sacred about the thought that life never truly ends, it only travels. Among biologists, the most electrifying question was whether any of the life aboard 3I Atlas shared ancestry with life on Earth. Could DNA, or something akin to it, be a universal code? Or would alien life rely on a different molecular architecture entirely? Without direct samples, no one could know for sure. Yet the ratios of certain elements, carbon to nitrogen, hydrogen to oxygen, suggested a startling similarity to terrestrial biology. It raised the possibility that all life in the galaxy might share a common origin, spread over billions of years by comets like this one. Humanity itself might be the descendant of ancient travelers, carrying the same spark now drifting past Mars. This realization rekindled an ancient humility that had long been lost in the age of technology. For centuries, humans had seen themselves as explorers, conquering the unknown. Now they began to see themselves as participants in a much older story, one written not by human hands, but by the stars themselves. The discovery redefined exploration. It was not about claiming territory, but rediscovering belonging. In observatories across the world, teams began preparing to detect future interstellar visitors. If one had carried life, perhaps others did too. Instruments were recalibrated to scan for the distinctive chemical ratios Webb had observed. Proposals emerged for intercept missions, fast propulsion probes that could rendezvous with incoming interstellar objects to sample them directly. The dream of touching life from another star was no longer fantasy. It was a logistical problem waiting to be solved. As plans took shape, humanity's gaze turned once more toward Mars. The red planet had always been a symbol of possibility, a barren world that might one day cradle human colonies. Now it carried a deeper significance. If traces of 3I Atlas's organic material had settled there, Mars was no longer merely a stepping stone for human expansion, but a potential sanctuary for interstellar life. The next rover missions would not only search for ancient Martian organisms, but also for new arrivals from the comet's tail. Instruments were redesigned to detect isotopic anomalies, to identify carbon chains matching those found in Webb's data. Each grain of Martian dust became a potential message from the stars. The general public followed these developments with reverent anticipation. For the first time in history, the distant world humanity planned to colonize might already be inhabited, not by native Martians, but by life from another solar system. Ethical discussions erupted worldwide. Could humanity rightfully settle on a planet that might now host foreign organisms? Would interference with their potential growth be a violation of cosmic order? Philosophers proposed that the event demanded a new moral framework, one not limited to Earth but extending across the stars. Planetary ethics became interstellar ethics. In religious communities, interpretations varied. Some saw 3I Atlas as divine confirmation that creation was universal, that life was the natural expression of a cosmic intelligence. Others viewed it as proof that existence had no single center, that every world was sacred in its own right. The discovery, far from weakening faith, deepened it. The divine, once imagined as distant, now seemed embedded in the very processes of chemistry and motion. The boundary between science and spirituality began to dissolve, replaced by awe. Even in the world of politics, the discovery reshaped priorities. Space exploration budgets expanded dramatically. Nations once cautious about funding deep space missions now saw them as essential to understanding existence itself. Cooperation became the new norm. The cosmos was too vast for competition. The International Astronomical Union established an initiative to coordinate all future interstellar object tracking. It was given a name befitting its mission, Project Continuum. Its motto, derived from a line in an ancient poem, captured the spirit of the era. That which travels between stars remembers all worlds. Under Project Continuum, new technologies emerged. Telescopes capable of detecting faint biosignatures at extraordinary distances were designed. Artificial intelligence, trained on the spectral fingerprints of 3I Atlas, began scanning archives of old data from other comets and asteroids. To the astonishment of many, subtle traces of similar patterns appeared in some records. Perhaps weaker, perhaps coincidental, but enough to suggest that interstellar visitors might have passed through the solar system before, unnoticed. The realization sent shockwaves through the scientific community. If this had happened before, could Earth itself have been seeded by such material long ago? Geological studies revisited the origins of life on Earth. Isotopic anomalies in ancient rocks, once dismissed as geological quirks, were reinterpreted through the lens of interstellar panspermia. Perhaps billions of years ago, a visitor like 3I Atlas had brushed past our young world, leaving behind the molecular blueprints that would evolve into every organism on Earth. The chain of ancestry now extended beyond planetary borders. Life on Earth was no longer a singular miracle. It was part of a galactic lineage. As this understanding deepened, humanity's relationship to the cosmos transformed from distant curiosity to intimate kinship. Each star in the night sky was no longer an unreachable point of light, but a potential relative, a home of life once connected through invisible threads of matter and memory. The night sky became a family portrait, ancient, scattered, but alive. The sense of kinship did not come without unease. Questions arose about what other forms of life might exist beyond the gentle biochemistry glimpsed in 3I Atlas. If one comet carried benign organisms, might others carry more dangerous ones? Could the galaxy host predatory forms of microbial life capable of consuming or replacing the chemistry of other biospheres? The thought unsettled even the most rational scientists. The universe was no longer empty, but that meant it could also be unpredictable. The very mechanism that spread life might also spread extinction. Still, curiosity outweighed fear. Humanity had always thrived by confronting the unknown, and this was no different. Laboratories on Earth began experimenting with simulated xenobiology, creating synthetic analogs of what 3I SAS Atlas's molecules might be like. These artificial compounds displayed unexpected properties. Some assembled themselves into membranes under freezing temperatures. Others generated faint electrical potentials in response to light. It was as though the building blocks of 3I Atlas's life were not only viable but versatile, capable of adapting to environmental extremes unimaginable on Earth. Scientists began calling this new class of biochemistry cryolife. Cryolife became a field unto itself, a study of life that thrives in cold vacuum and radiation. It inspired new approaches to bioengineering, medicine, and even materials science. The molecular stability of these hypothetical organisms hinted at innovations that could revolutionize human technology. Polymers that repaired themselves in vacuum, solar membranes that mimicked the light-harvesting compounds found in Webb's data, all were derived from the template of the interstellar visitor. The frontier between biology and technology blurred as humanity learned from a teacher born between stars. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on 3I Atlas possibly carrying life toward Mars? We want to hear from you. Thank you for watching and see you next time.